we proceed with steady state errors. Okay, for this chapter, what you need to know is you have to know about the test signals. So far, we have learned about stat, ramp, as well as the parabola. And for this step, you have learned the time function is 1, and then if we have Laplace, it's 1 over s. And for the ramp is t, and its Laplace is 1 over s squared. For the parabola is half t squared, and for this Laplace transform is 1 over s cubed. And for this purpose of the course, we limit our study or our discussion on the stable system, where the natural response approaches 0 as t approaching infinity. Means that we have the systems that is the response, the natural response is the response caused by the systems, means that it will dies out over time. As t approaches infinity, the natural response will become approaches 0. Okay, for this plot here, we can see that, for example, here we have this is the input. This is the input step, and then this is actually ramp function over here. So you can see here, this is the input. We have output 1 and output 2. For output 1, we can say that it has 0 steady state error. Why? Because at a steady state, the value of the response here is the same as the input. Means there is no error at all. For the output 2, you can see that there is a finite value. Means that we can calculate the input minus the output, we can get some value for it. So finite means it is we can represent it in numbers. Okay. As well as for the RAM input here, so this is the input. Okay, for the output 1, this line is actually converged, and finally at steady state value, the error is becomes 0, because the at steady state final value is the same as the input. For output 2, it becomes constant after some time. So we can say that for this second output, it has finite value of error. Means that we can calculate input minus output, it gives some value. However, for output 3 here, the value is actually diverged from the input, because as t approaching infinity, we can say that it goes to infinity. When we do analysis for this steady state error, what we consider is we consider this kind of plot diagram, where we have a system GS and we have a unity feedback system. So we have GS, and then we have HS equals to 1. In this discussion, we will limit our focus to the steady state error that arise from the configuration of the system itself. And the type of applied input means that it purely comes from the design of the system itself, from the GS. Okay, let's try to come up with a steady state error in terms of GS. Okay, for this system, we have a GS plan, we have a unity feedback system, we have error ES, we have input RS, and we have output CS. And we know that from the diagram, we can come up with this equation. We know that ES is actually input minus output. Okay, so this is the input, this is actually the feedback that brings the output. Okay, so ES is actually RS minus CS, and CS comes from the error multiplied by the plant GS. So we have CS equals to ESGS. Okay, so we can come up with term of error in terms of GS, which includes the input that is supplied to the system and the plant itself, GS. So what we have is actually we put the equation 2 into 1, where we will have these terms ES equals to RS, and then we have CS is actually ES GS, and then you can rearrange the equation to get this term. ES equals to RS over 1 plus GS. And then we apply the final value theorem. So you can see in the Laplace in the previous lectures, I have supplied the table of Laplace. You can see the final value theorem, where the error when the time approaching infinity is we can use the limit t approaching infinity of et. So we convert it to Laplace using the final value theorem. What we have is actually limit s approaching 0 as es. So we convert the es into the equation. What we have is this term. So ESS equals to limit s approaching 0 of SRS over 1 plus GS. So we will use this equation of steady state error in the next our discussion on the different type of inputs. This is the input, okay? So we have step, we have ramp, and we have parabolic input. For the first example here, determine the steady state error for unit step response of the following system. So we have the system GS equals to KS plus 2 over S plus 1, S plus 3. So this is the gain. We can find the output is YS equals to GS RS. So YS is the output, RS is the input. Let's say we have, in this case, is a unit step response. Unit step response means 1 over S. So we introduce 1 over S, S for the RS. So we can find a value of K1, K2, and K3 over here, where you can find it as a 2K over 3, K over 2, and negative K over 2, and negative K over 6. That is depicted in this equation here. And finally, what we can do is we apply the inverse Laplace to the equation here. What we have is actually we have this term. When we want to find the steady state error, we need to find the steady state value. Steady state value means at t approaching infinity. Okay, so we apply limit t approaching infinity to the output yt. So this when we have this exponential term, when we have t approaching infinity, this t approaching infinity, what we have is actually 0. K2 over 3 minus 0 minus 0. What's left is we only have this term. Therefore, we can find the steady state error, which is the input minus output. So in this case, this is the input RT. This is the output at the time approaching infinity, which is at the steady state or the final value of the output. So we have 1 minus 2k over 3. So why we use 1? Because it's actually unity or unit step response. Unit step. Unit step means 1 over S. Next example, we find the steady state error for unit ramp response. For this following system, we have GS equals to 1 over TS plus 1. So similar to the previous example, what we do is we find GS RS. So in this example, we have 1 over S square, because this is a unit ramp. So we can divide it, we can find the coefficient using the partial fraction, and we find value k1, k2 and k3, and we get this equation. We apply inverse Laplace to this equation. What we have is we have yt equals to t minus capital T plus capital T exponential negative t over capital T. So we can find the final value or steady state value of the system by applying the limit t approaching infinity to this output yt. Thus we have here these terms approaching infinity means equals to 0. So t minus capital T plus 0. So what we have is actually only t minus capital T. So we can find the steady state error by put it in this equation. Input minus output, we have t minus t plus capital T, which give you the final answer of t. Now we proceed with the next one, system type. System types is very easy. You factorize every denominator and you find the poles at origin, which is in this case here and here. Poles at origins mean s equals to 0. So the system types is depend on the power of poles at origin. In this case, this is type 1. This is type 3. This is actually s power of 1. This is s power of 3. So type 1, type 3. We go back to the equation that we have derived using the final value theorem, which is this equation, okay, to find the steady state error. For the step input, Rs is equals to 1 over s. So we replace 1 over s in this equation. What we have is actually we can cancel out. What we have is a steady state error equals to 1 over 1 plus limit s approaching 0 of gs. Okay, for the step response, this is the step input. Okay, step input, we have this is a system type. Let's say we have type 0, type 1, type 2, type 3. Okay, for the step input, only a system type 0 give you a finite value. If you have higher order system, type 1, type 2, type 3, type 4, and so on and so forth, what you get is actually you get the steady state error of the system will be steady state response of the system due to the step input is equals to 0. Okay, to have 0 steady state error, okay, we want steady state error to become 0, you need to have 1 over infinity, because 1 over infinity equals to 0. Because this term is actually 1 plus limit s approaching 0 of gs, so we need to make this term becomes infinity. How do we ensure that we have a limit s approaching 0 equals to infinity? Let's say we have a system 1 over s plus 1, s plus 5. What type of the system here? Type 1, because the power of s origin is 1. When we apply limit s approaching 0 of this gs, what we actually have is s approaching 0, s approaching 0, s approaching 0. We have this term become 1 over 0, 1, 5. Which equals to 1 over 0 equals to infinity. Let's say we have the same system 1 over s3, s plus 1, s plus 5. What is the type of the system? Type 3. So when we apply limit s approaching 0, what we have is 0, 0, 0. Actually, it becomes this term as well. So we can say that we can summarize for system type greater than 1, means 1, 2, 3 until n, the limit s approaching 0 of gs equals to infinity, and it will give you the steady state error equals to 0. That's why when you refer back to this table, if you have a system 1, 2, 3 and greater than 1, the output, the steady state error is equals to 0. Okay, now let's see for type 0. Okay, let's see the type 0. So from this table, type 0 will give you a finite value. Let's see how we get to this. Okay, for this type 0, we have as power of 0 equals to 1. So we have a system, regardless of the system, we have a type of 0 here. As power of 0, we have s plus z1, s plus z2, z is 0 over s plus p1, s plus p2, p is poles. So what we have is actually we have gs equals to this term, and when we apply limit gs to this term, we have z1, z2 over p1, p2, which give you some values. It gives you some finite values. So we can say that for the type 0 system, it gives you some value, 1 over 1 plus some finite value will give you some finite output. So that's why from the table here, you can see that for type 0 system, it will give you output which is a finite output. Okay, next let's see the input for RAM signals. Okay, similarly, when we use this equation here, we replace the value of Rs equals to 1 over s square. Inside we have this term, and when we can rearrange, we will have this term. We have this term when approaching 0, is actually we can just ignore this term s here. We have this term 1 over limit s approaching 0 of sgs. Okay, so for the RAM input, it gives you 3 different types of output, which is infinite steady state error, a finite value of steady state error, and 0 steady state error. For type greater than 2, so actually what we want is we want the term to be infinity. This term to be infinity. Limit s approaching 0, sgs equals to infinity. How to do it? What we can do is actually when we have a system, let's say we have a power of 2. Okay, we have a power of 2, and then we have a gs, sorry, not gs, we have another term, let's say s plus 1 over s plus 3, s plus 5 over here. Okay, so this is actually the system type 2, because we have the power of 2 of s here. Alright, so when we put it into the this term, we have limit s approaching 0 of s, and then we have term here s plus 1, s square plus s plus 3, s plus 5. So s approaching 0, actually we can cancel out this one first. Cancel, and then we can put s approaching 0, s approach 0, s approach 0, s approach 0. The terms become, okay, so it becomes 1 over 0, 3, 5, which is 1 over 0, which is equals to infinity. Okay, you can do a similar analysis for RAM input, type 2, type 1, type 0. You can do similar analysis that we have done previously, and then you can see what are the relationship between the type of the system and to the steady state error. Okay, and you can do the same for the parabolic input. But now parabolic input, Rs is equal to 1 over S cubed. So you can put it into this equation. And finally, you can get this term for the steady state error. And what we want to see now is the example. Okay? Example here. Let's say we have these problems. We have a system at figure 7.5. Here we have GS equals to 120 S plus 2 over S plus 3 S plus 4. Okay, so the question asks you to find the steady state errors. Okay, find the steady state errors for inputs of 5 UT, 5T UT, 5T square UT. Okay, means this is the step. This is the this is step, this is RAM, this is parabolic input. Okay, so how do we do it? Okay, what we can do is just we use the equation that we have found, which is for the step is 1 over 1 plus limit s approaching 0 of GS. Okay, this is ESS for step input. For the RAM, we can use 1 over limit s approaching 0 for SGS. And for the parabolic is we use ESS for parabolic equals to 1 over limit s approaching 0 of S square GS. Okay, so for the step input, we use this equation. Since it is not unity, it is not unit input, because we have 5 here, 5, 5, 5, meaning that for step is actually 5 over S. It's 5 over S. So we put it into the equation. We have 120 S plus 2, we have S plus 3, and we have S plus 4, and we have the term for RS. Okay, for the step input is actually here. Okay, what type of the system here? So this is type 0 system, because we don't have S at origin, which is S actually power of 0 equals to 1. So that's why we have type 0. So we know that if we have type 0, for the step response, we will have a finite value. This is type 0. The input is step. What we expect is we have steady state error equals to finite values. So we calculate, for the example, we approach limit as approaching 0, approach 0, approach 0, approach 0. Actually, we have 120 multiplied by 2 over 12, so we get 20. So 5 over 1 plus 20 equals to 5 over 21, which is a finite value. The same goes for RAM input. For the RAM input, we use this equation. So limit s approaching 0 of SGS. So SGS, as our G is 120 S plus 2 over S plus 3 S plus 4. So limit s approaching 0, approaching 0, approaching 0, approaching 0, approaching 0. What we get is 0 multiplied by some values equals to 0. That's why we get this 5 over 0, which is equals to infinity. And you can do the same for the parabolic input. And then we will get is 10 over 0 equals to infinity. I think that's it. Because I have shown you these examples, I think you can do these examples and these examples on your own later on when you go back and do some revision. Please do it for the sake of your understanding. Okay, do it, and then if you have troubles understanding how this example come up with this solution and this solution, you can just get back to me and I will explain it to you.